deep learning on the internet's edge. And then continuing with a further discussion beyond the actual 5 or 6 pages of the paper itself into more technical details associated with implementation and how you bring up this type of system and limit its performance and scaling before concluding. So, one second. So the premise behind why we want to build new computers is kind of shown here. Machine learning is really ubiquitous in our daily lives today. So in applications like machine vision and search and e-commerce, natural language processing, game playing, and even chatbots, machine learning has become the de facto standard as an algorithm by which we interact, by which we perform these tasks. So when I create a self-driving car and deploy it in the field, and you can find these cars in numerous cities today, autonomously driving around, the way by which they make sense of the world around them is by using machine vision algorithms. It's not algorithms that cherry pick features from images by human-made algorithms. It's really machine learning models or deep neural networks that are able to take those images and infer features from them based on statistical data. The power of these machine learning models has given us orders of magnitude improvement in the performance of any of these tasks and a host more tasks that are really advancing the forefront of what we can do from an algorithms perspective. Today, how we access and make use of those machine learning models is typically those models need to access data taken from sensor devices. So these could be, for example, lightweight sensors such as cameras, microphones, wearable devices, wireless communication systems, routers, really anything in the field that's generating data is the thing that's trying to deliver information to that machine learning algorithm. But in contradiction to that, we have these milliwatt class sensor devices, but in order to make sense of that data with these best algorithms, we run that compute on kilowatt class computers, right? So these are your NVIDIA GPUs, custom ASICs from like Grok or Google, or even in the top right here, you can see the Cerebrus wafer scale computer, which is a tens of kilowatt class computer. And so this disconnect between the way we generate data and the way that data is being consumed to make sense of it really limits applications of how we implement machine learning in practice. I can't run this kilowatt class algorithm on my milliwatt class payload device. To give you an idea of the state of the art of trying to blend these two worlds together, this is Google's Edge TPU. It's a Google had made a custom CMOS ASIC that's able to be co-located next to your camera to be able to do recognition of images that are being generated. And this consumes many orders of magnitude more power than the camera itself. So this is a couple watt to tens of watt class ASIC. You know it's not power efficient because it has this large heat sink on top of it, which means it's not thermally efficient at all. So let's crack open those models and figure out exactly why they're forcing computers to consume kilowatts of power. So if I take a modern machine learning algorithm, this would be, for example, a transformer model like what you would run ChatGPT with, and tear it apart, what I'll see under the hood is that it's running many successive layers of neural networks. And at its basis, these layers are composed of two elements: a linear part, which is matrix vector multiplication, and a nonlinear activation function, which is able to take the result of matrix vector multiplication and do some nonlinear processing to it before allowing us to successively apply these layers. So being concrete, here's an example of a K-layer deep neural network, where we start with a vector. These could be, for example, the pixels of image, x0, and we do a matrix vector multiply through the weight matrix W1. before applying the nonlinear activation function f. This generates an output activation vector x1, which then we can successively apply the next layers to until eventually we end up with the final set of output activations xk. And typically you'll have some figure of merit, like for example, the maximum value of this, which will be able to tell you which bin your image falls into. For example, is this a cat or a dog? Diving in and looking at what the hard part of this algorithm is, you can see that I have only a couple of elements I need to do my nonlinear activation function to, but I have this enormous matrix vector multiply I need to do that needs n squared computations. And so in particular, looking at that matrix vector multiply, I can algorithmically describe this as a sequence of two nested for loops iterating over the two dimensions of my matrix that perform a multiply and accumulate operation onto my output activation vector from my inputs. And typically we use something like a compiler. In the case of NVIDIA, this would be CUDA, for example, that's able to take this algorithm and map it efficiently onto the instruction set of the hardware. Now, the issue with what I just showed that's forcing us to have these computers be kilowatt class is that the size of these machine learning models is growing exponentially. So here's a plot I made that ends circa 2020, because it's when the paper came out. But it kind of illustrates a point, which is that the number of model parameters in machine learning models, this is the number of weights, is growing exponentially and is roughly doubling at a rate of every 3 months or so. And so the number of weights in my model is doubling, which means that the size of my matrix vector multiplies is growing, and the number of layers I have is also growing. So it takes longer for me to do my individual computation of layers. I have to do more data movement, move more data around in order to keep that data local to my compute and do the matrix vector multiply. And then I need to do more layers, which means I have a higher latency of getting my result out. And so here's a quote that's quite old at this point, actually. That's from the CEO of Cerebras, which was predicting that GPT-4, which is now in deployment, will have 100 trillion parameters or so to be able to run ChatGPT. So there's an exponential growth on the algorithm side of things, but what's wrong with digital computing? Why can't I just make my chip larger and be able to scale to continue running those algorithms? And the reason why is subtle. And it's not as simple as the media will tell you, where we can just say Moore's law is dead and call it a day. You can actually look at trends in the semiconductor industry and just look at, for example, the number of transistors that we can cram onto a chip. And for the most part, if we look at the trend in the last decade, we can kind of make the statement that Moore's law is not necessarily dead. We're certainly able to keep up with a commensurate exponential growth in the number of transistors we can cram into a given area of silicon. However, what those additional transistors give us is not necessarily an advantage. And so you see figures of merit such as clock speed, how fast I can do single-threaded execution of computation on that chip, have flatlined. And the reason why those figures of merit have flatlined is fundamentally because of thermal power dissipation. I'm not able to sink enough heat away from my chip. So my heat density of my CMOS is stuck at a fixed number. And this is because of a breakdown of what's called Dennard scaling. Dennard scaling was the notion that when I went to my next transistor node, the energy to flip a CMOS logic gate dropped in size proportion to the shrinkage of the transistor. So my thermal heat flux of my CMOS node stayed roughly the same as I kept shrinking my transistors. That scaling broke down in about 2007, 2008 or so. And as a result, the thermal power dissipation of chips has just grown exponentially. Now, the reason why machine learning in particular is very hard is actually not because of logic. It's not compute. And you can kind of see this if you look at this review paper from Vivian Z. She's a professor at MIT who is an expert in designing custom ASICs for machine learning. And what they analyzed is they looked at the cost of the individual components that built up ASICs for doing machine learning. So here, ALU is arithmetic logic unit. This is your basic multiply and accumulate operator. And then everything below this is the cost of data lookup and movement. So for example, RF is a register file here. This is in this case, this is a kilobyte class register file that's located right next to your multiplier. And then buffer would be some like local cache, and then DRAM is an off-chip memory that we access. And you can see that the cost of just doing my multiply and accumulate operation is the same as actually just getting data from a register file located within a few tenths of microns of that multiplier. And immediately alarm bells can start going off in your head to realize that compute is likely not the issue here. It's actually data movement. And indeed, you see that when you go to moving data from off chip onto chip, the cost of getting a single value to that multiplier is about 2 to 3 orders of magnitude higher than the cost of the multiplier itself. And so that's why when you look at the best CMOS ASICs and look at where is my power going to run these machine learning models, on the order of 80 to 90% of it is just in data movement, and only 10% goes into the payload operation of doing compute itself. This is referred to as the so-called von Neumann bottleneck, where we're limited by bandwidth, not necessarily computation. And so that fact has really spurred on research into a host of other approaches to doing computing that aren't necessarily limited by that bottleneck. And so here I'm just going to highlight a number of fields that aren't just optics necessarily, that are making really good strides at trying to advance doing different forms of computing. So in the top left here, I'm showing a paper in Nature that comes from Stanford, where they're building in the back end of line of a traditional CMOS process, resistive RAM cells in large arrays. And what these cells are able to do is they're able to build what's effectively called a memristor crossbar array, where they can tune the values of these resistors over several orders of magnitude, and do single clock cycle execution of vector matrix multiply through that resistive RAM cell. And so long as they don't have to update these resistor values often, they can keep those weight values local without significant data movement, and pipeline matrix vector multiplications through the entire system. Other electronic type approaches include ionics. This is a paper that comes out of MIT in recent years, where they're able to build very energy efficient ionic processors, where the method of computation here is not necessarily like a resistive filament, but actually just an ionic channel that has some electronic conductive properties to it. It's quite promising. An approach taken by Intel is to, rather than just trying to directly mimic the algorithm of matrix vector multiply onto hardware, at a higher level, the thing we really want to mimic here is brain activity, right? The de facto standard for being able to do any of these applications or algorithms is actually the human brain, where the human brain consumes on the order of 20 watts or so, as opposed to these kilowatt class computers, and is better at all these algorithms than the actual algorithms we're designing now. So if we could mimic the actual dynamics of the human brain, in principle, we could have better energy efficiency and higher throughputs. Everything sounds better. So as an initiative to do that, folks work on spiking, or what's called neuromorphic computing, where they try to build analog hardware to mimic those dynamics. So here, Intel has custom CMOS ASICs that have billions of transistors on them and millions of synapses, artificial synapses, that create those spiking type behaviors, and can they try to map the types of algorithms like ChatGPT onto this hardware, and create the same performance as deep neural network algorithms. Now, these electronic approaches are all very interesting and exciting and show a lot of promise, but today we're going to be focusing on photonics. And so here in the bottom right, I'm showing two examples of implementations of how you would do matrix vector multiplication in photonics, where the bottom paper or the left paper comes from Dirk England's group at MIT, and essentially creates a 2D array of Mach-Zehnder interferometers to allow you to encode those weight matrices onto a chip, and then you can pipeline a vector of input activation values into one side of the chip on the left and read out on the right side the result of the computation. And then work from Feldman et al. Seeks to scale that by realizing that, hey, we can do wavelength division multiplexing of these types of broadband components. And so they don't necessarily use Mach-Zehnder interferometers here, but they do wavelength multiplex an array of photonic components that allows them to get high parallelism and high throughput through the system, which is quite exciting. So why would we be talking about photonics at all? In fact, there's a lot of reasons why you would not consider optical computing as a method to do. In particular, certain parts of certain functionalities in electronics are easy, right? Natively, nonlinearity is very easy with transistors. The inverter is a sub-femtojoule per flip kind of device that has high nonlinearity that's given rise to the benefits of digital logic, etc. Electronics gives us memory essentially for free, and gain is very easy. Whereas in photonics, in any material platform, nonlinearity is typically incredibly weak. We have to fight very hard to build nonlinear photonic systems. Memory is also incredibly hard. Photons are traveling wave dynamics and want to escape your system as fast as they can. And gain is possible to find in certain material platforms, but also just very energy inefficient. But there are downsides to electronics, as I mentioned before. And so you can see that in electronics, communications and fanning out data from a single location to many locations has CV squared type energy costs or length-dependent energy costs that become prohibitive at distance scales beyond, let's say, millimeters or so. Whereas in photonics, waveguides and fibers give us essentially length-dependent interconnect costs. I can communicate just as well in photonics at millimeter scales as I can at kilometer scales because of the essentially lossless nature of fiber. In addition, fan out is very easy through near lossless beam splitters and combiners. And because of the work I've shown on the previous slides, we have proof of concepts to say that linear algebra in electronics is hard. Trying to do matrix vector multiply is hard, but we believe that linear algebra in photonic platforms is quite easy, as long as we're okay with accepting moderate to low precisions on the order of 8 to 10 bits, which is suitable for machine learning applications. Before I dive into the talk a bit more, I just want to say that this field is not a new idea. It's been going on since the 50s or 60s, where you can see papers by Sludds, I swear they're here, in circa the 80s and 90s, and even papers before then where folks were looking at how they can create optical systems that do computation. And this prior work really begs us to ask the question of, why are we talking about doing optical computing again? Why now? And the answer is a lot of things that killed optical computing back in the 80s and 90s are no longer true anymore. The thing that really stopped folks like Sludds working on optical computing in the 90s was digital CMOS was growing, continuing to grow at a factor of 2 every year or 18 months. And that exponential growth really killed the lack of exponential growth in optical systems. What's changed now is that exponential growth has essentially stopped. And so now we have enough data to make the algorithms work. We certainly have enough digital computing to do any side processing that needs to happen. Photonic integrated circuits that are mass manufacturable exist. We know deep neural networks work, whereas before we really didn't know that these were an algorithm we wanted to run. And we know that von Neumann architectures are probably not the optimal way to run artificial neural networks. And so this brings us to the approach we want to take, which is we want to use, for here, integrated photonics as a means of doing computation. And so for folks who don't know what integrated photonics is, I want to give you an idea of what you can mass manufacture in CMOS foundries today. Here I'm showing an example of a silicon photonic chip that you could get made at CMOS foundries, where we can monolithically integrate 3-5 materials, silicon photonics, and transistors on the same platform. Here is an example of, for example, a 3-5 laser that's, for example, creating an optical frequency cone, driving into a wavelength multiplexing system that allows us to drive simultaneously many applications. In this case, this one chip has an off-chip interconnect through a high-speed Mach intermodulator, an on-chip interconnect, and is driving a LiDAR system. So this LiDAR system consists of some amount of beamforming and phase shifting, in addition to having a 2D array, a 2D receiver array. Now, because this is silicon, and we have transistors in the platform, you can add a host of other side features that you could not have in any other material platform. And so you can integrate CPU and ARM cores to do processing right next to your waveguides. You can have 2D image sensors like cameras located in the same silicon substrate, any analog or digital logic, really. And then the final photonic application I'll mention is you could have, for example, these photonic processors, right? Here's an example of an MZI crossbar array, but this could be any photonic coprocessor that we could think of with all of its integrated electronics that's required. And then me shelling why silicon photonics is so great is really there's a revolution that's been happening for the last couple of years. Just in terms of dollar amounts on the communication side, Cisco purchased Acacia for several $1 billion a couple of years ago to do coherent comms in silicon, and that's been working quite well for Cisco ever since for deployment outside the data center. And then startups like Lightmatter and IR Labs have been creating co-packaged optics solutions that give unprecedented bandwidth and energy efficiency to communications for your ASIC outside the package. Beyond these, silicon photonics is also being deployed in computing, sensing, quantum computing, and LiDAR in high volume today. So let's get into the actual talk here. So our story about running machine learning computation on sensors really starts with this picture, where the way that we're doing the computation today is kind of shown on the right of this diagram, where a smart home device, this could be your Google Home or your Amazon Alexa, they listen to a voice query, such as what is the height of Mount Everest? And that voice query gets formatted as a vector U, where that vector is then sent over traditional fiber networks, communication networks, to an ASIC computer located in the cloud. This is hundreds or thousands of kilometers from you, where that query gets to the back of a queue, an algorithmic queue, where it has to wait until it gets to the front of the queue, gets computed on. The resulting output V for the height of Mount Everest is sent back to you through those communication networks, and then read out through the smart home device to you. This entire process takes quite a long time. When you ask Alexa or Google Home a query, it has to think for several seconds as it sends that query off and has to get processed and come back, because it's not doing the computing locally. That lack of local computing really prohibits a lot of applications, like being able to do best-in-class computing on, for example, self-driving cars. Now, what we're going to propose to do today for edge computing, the notion of computing on these sensor devices, is we're going to take that process of shipping U to the server and V back, and instead swap it on its head and take the weight values, the weight matrix W, and ship it to the sensor device, where the compute can happen locally on the sensor device with very high energy efficiency. So diving into that, I'm going to look at these little red pucks here, which we're going to call a smart transceiver. These are photonic integrated circuits that are specifically designed to encode weight matrices in an analog format onto the optical domain. So here you can see, again, I'm showing the layers of a deep neural network, where one of those layers has its weight values W being cast through digital to analog converters onto optical modulators, where the values of those weights are encoded onto the intensities of different wavelengths of light. So being explicit, if I had my weight matrix and one of the weight values is 1, the intensity of my laser would not be attenuated on this time step. But if my weight value was 0, then the modulator would be set to like full attenuation and turn the light off. So we take this weight matrix, we're going to cast it onto onto the different wavelengths of light here. The way by which we're going to do this is shown in part D of this figure, where we're going to take that 2D weight matrix and cast it into a time frequency basis. So the individual rows of the weight matrix are going to map to different wavelengths of light, and the columns are going to map to different time steps here. Now, the reason why we choose to do this approach is, first, we know that optical fiber and generally photonic integrated circuits are incredibly broadband. And so typically the amount of bandwidth that we have available in the optical domain is on the order of a few tens of terahertz that we can use. And so what's standard for telecom folks to do today is they'll take that terahertz of bandwidth that they can reasonably use, and they'll chop it into a bunch of channels or bins. And so each channel might have 100 gigahertz or so of bandwidth that we can utilize. You end up with about 100 to 130 channels or so in the optical C-band that you can utilize for encoding these weight values. Time multiplexing has a big benefit. First, it allows us to scale to incredibly large matrix sizes. But second, it also enables us to make use of time integrating receivers. And so on each time step here, if I just look at a single column of the weight matrix, I have all these wavelengths of light coming into my receiver. I only need to apply encode a single input activation value x1 on the first time step onto them. And so I only need to actuate one single broadband optical modulator, that's a Mach zehnder interferometer in this case, to encode that value. And that makes my client device, the sensor, very energy efficient, because I only need one single active optical component that I'm actuating to do all the computation of my best-in-class machine learning models. After encoding my input activation value onto the modulator, I then split the wavelengths out using a wavelength division multiplexing device, and then we time integrate. And so what this time integration is going to allow us to do is to sum up all the partial products of this vector matrix multiply to create the output activation value y on these outputs here. Similarly, the other immediate benefits we can kind of see here are that I really only need a single copy of high-speed active analog components. I only need one high-speed DAC. This is a gigahertz class DAC, and one high-speed ADC. And if there was any kind of slide I really wanted you to look at for the talk to make sense of what the benefit of this research is, it's this one. We're looking at this client sensor device, and we're trying to figure out how energy efficient this is. And the key innovation that's happened here is we're only actuating a single active optical component to access that tens of terahertz of bandwidth, memory bandwidth that we can stream into the system. And using time division multiplexing to have very slow readout electronics of the results, and then only keeping a very local memory here for the input activations to get the results of computing the system. And so as a result, we're amortizing the cost of these typically high-cost devices like DACs, ADCs, and modulators by factors of n or m in the vector matrix multiply size, where n and m are typically on the orders of hundreds or thousands here. And so as a result, the costs in silicon photonics today of using these devices are typically picojoule per use, but we're amortizing them factors of n or m. And so the actual cost of a system we could build now would be on the orders of 1 to 10 femtojoule per multiply in a cumulative operation, without new materials or or any really new development that needs to occur on the client side. All this is possible in existing CMOS technologies. So again, just hammering home the point here, we're able to access terahertz of optical bandwidth using a single gigahertz class optical modulator with megahertz class readout speeds. Okay, so theory is all well and good, but you need to actually build the damn thing and show that it works. And so this is where an entire PhD of effort goes. And so here we experimentally demonstrated all of the aspects of this system and showed that indeed they do work and scale like they would think they should. And so I mentioned that there were 3 parts before. We need a smart transceiver to encode all of that weight data onto the optical domain. We're going to need some kind of optical link to connect that smart transceiver to our client device, and then we'll need to build that client device as well. So here we're making use of a smart transceiver that's made in a traditional CMOS foundry process. This is a silicon photonic smart transceiver composed of 48 50 gigabit per second Mach center interferometers. These are carrier depletion modulators that are capable of that combined have a total bandwidth out of the chip of 2.4 terabit per second. You can see, for example, here, wide open eye diagram at 50 gigabit per second NRZ encoding of these modulators. And an example of 16 lasers going through the chip simultaneously shown here. We also need a link. And so you could do this with a fiber spool in the lab, but we picked to do something a bit more ambitious. And we made use of 86 kilometer of real-world deployed fiber that goes from our lab at MIT to MIT Lincoln Laboratory. This is a real-world fiber that snakes throughout the Boston area and has all of the complications associated with using real-world fiber, including poor splicing losses from decades of being in the ground and breaking and reflection, polarization drift, etc. And so you can see a rough sketch of how this fiber's path looks throughout the Boston area here. And then finally, we need a client device. And so here we're making use of commercial off-the-shelf components, namely a commercial off-the-shelf lithium niobate modulator and fiber wavelength division multiplexing device with custom homemade electronic time integrating receivers that I made that'll enable us to do that readout of the accumulated signal. And you can see an example of integrating a fixed amount of optical power here, shown in the bottom figure. And so when you take all these components and you build them together, you can see a quick demonstration of how this system looks in this figure. Here, I'm showing the weight data coming out of the chip for 3 different wavelengths of light being encoded. Three different vectors being encoded onto the chip simultaneously. And while these weights are flowing through the system, we're going to follow the data path of lambda 3 here, just to make sense of how the computation is happening. We're going to be doing classification of digits here, where these pixels that are highlighted for the digit 3 are being encoded onto the broadband optical modulator, the lithium niobate modulator. And if we look at after that multiplication, what is coming out of the integrator, we can see here's the output of just the modulator, the input activations. Here's the result of the multiplications of weights and input activations, generating output activations. And here's the time integrated signal where it's accumulating the area under these curves in the electronic domain at slow speed. If we do random computation of floating point values repeatedly, many times, we can try correlate how well does this calibrated optical system do against digital ground truth. And so you get a plot like this, where ideally you want it to be a straight line, saying that if I generated a optical value y and I compared it against y hat, they should have the same value. And so deviation from that straight line is error in your computation. So here, if we plot that error, we see that we have an error, a sigma on this that's on the order of about 8 bits precise or so, which we know is sufficient for machine learning computation. Indeed, if I just look at the output of classifying this digit 3, you can see that the machine learning model has a big spike on 3 on the output, saying, in fact, it is a 3. And as a testament to how good the system computes and how good the model is, we show that both over a local fiber deployment using 3 terahertz of optical bandwidth, and over that 86 kilometer of deployed fiber, we can have close to 99% image classification accuracy, which matches the ground truth of the model. And so all this demonstrates that this proof of concept can work with high optical bandwidth in real-world deployed systems. Now, this is all well and good for proving our kind of proof of concept here. But along the way of doing this research, we kind of figured out a couple of side benefits to some approaches that we've taken that were quite exciting. And so I'm going to nerd out for about 5 minutes about time integrating receivers, if you'll allow me to. And so here I'm showing a couple of different types of photodetection and how they perform as a function of optical energy per multiplication for these different types of photodetectors. So traditionally, when you build an optical communication system, you're limited by one of 3 sources of fundamental noise, right? You have thermal noise of your receiver. This is how good your electronics is, and how well you closely integrate electronics and photonics together. You have shot noise, which is just inherent to how many photons I have per shutter window, per unit of time integration. And then you have laser ring noise, which typically is not what limits you for optical communications. Here, I'm plotting the performance of thermally limited receivers, where these 2 right curves are examples of traditional thermally limited receivers. So these are photodetectors hooked up to transimpedance amplifiers that you can buy off the shelf today, where you can see that they're kind of limited to the 10 to 100 femtojoule per multiplication energy efficiencies to reach high image classification performance. Now, if you're an optics person, the first thing you might say is, well, I know how to overcome thermal noise of electronics. I can create gain on my optical side by making use of avalanche photodiodes. And so here's an example of using linear mode APDs to get gain over that electronic thermal noise. And you can see there's about a 10 or 20x gain, which is the gain of the APD here in noise performance. That gets me down to the hundreds of attojoules of energy efficiency per multiply and accumulate operation. But the big downside of using APDs in practice is that you need incredibly large reverse bias voltages, typically like 10 or 20 volts on these APDs, in order to bias them in a regime where they give you sufficient gain. And so because of that, just from an I times V argument, the power consumption of these circuits ends up being enormous per multiply and accumulate operation outside of the actual cost of the optics, the actual cost of the photons. Now, in blue here, what I'm plotting is the energy efficiency of the time integrating receivers that I made in the lab, right? These are commercial off-the-shelf components. This is by no means fancy or state-of-the-art for what electronics could do, but simply showing that when you do time integrating receivers, you only see thermal noise one time when I do readout. I only see KTC noise one time after doing 100 multiplications. And so as a result, I can amortize that thermal noise over an entire vector multiply. As opposed to in these rightmost cases where I see thermal noise for readout on every single multiplication. And so as a result, I get 100x improvement or more in energy efficiency per multiplication in the case of for the case of these time integrating receivers. And this is with circa 1995 electronics. This is by no means state of the art. And so this made us question, these things are so sensitive. What's the limit of that computation? So again, thermal noise for a readout window scales as root KTC, where C is your receiver capacitance. T is temperature. In commercial practice, this is not going to change from roughly room temperature, and K is Boltzmann's constant. And so if you take the roughly 10 picofarad integration capacitance that I was using in the lab with that old electronics and scaled it down to what you can make with CMOS electronics today in the 1 to 10 femtofarad regime, you leave the thermally limited regime and enter the shot noise limited regime, where back of the envelope napkin math tells you that the number of photons you need per multiply and accumulate operation reaches less than 1 photon per multiply. And that got us kind of interested in the fundamental physics of what's going on there. And so we did a laboratory demonstration where we built the same kind of setup with weights and inputs going through a weight and input modulator, and shining into a superconducting nanowire single photon detector in a 0.8 Kelvin cryostat. And you can see that indeed this receiver is perfectly Poissonian limited. Here's in stars measured data from the receiver for Poissonian statistics, and it perfectly matches with theory. And when you do computation on this type of system, you can see that indeed you can have very good classification accuracies for the same model we were doing before with less than 1 single photon per multiply and accumulate operation. So what does that mean? And there's a way to think about this that doesn't sound like sci-fi nonsense. Here I'm showing a cartoon of like input and weight vectors going through a system to do 30 multiplications of work. And they produce the product vector shown below here. Now, if you map those product vectors to a probability of generating a single photon pulse, you might end up with pulse single photons that distribute like this in time. And if you time integrate that signal, you get something like this, where even though I only have a half a photon per multiplication, I accumulate 15 photons for my output activation value. And so the final thing, the final value I read out from the system is shot noise limited to an SNR of let's say 3.8 or so, which is much larger than 1. It's because you're accumulating photons by doing time integration, you have a high signal to noise ratio, even though at every step along the way you had a signal to noise ratio less than 1. And so that's fundamentally what this less than 1 photon means. Now, the point of this is to not say that everyone should go be putting cryostats into their system. The point is to really say that there's promise here for doing shot noise limited computing in existing electronics, advanced node CMOS with photonics and electronics. If your receiver can be 1 to 10 femtofarad integration capacitance. Now I know I'm running out of time here, so I'll briefly discuss these in the next few slides. But if folks have questions, we can gladly come back to it, and they'll be in the notes that are shared out. So we had thoughts when we were kind of writing a paper about how does noise scale for different architectures? How does bandwidth scale as you increase the number of wavelengths, like stuff like this? And so we kind of detailed this in the supplemental, but it's good to just kind of talk through that work. Here's an example of how you might build the netcast system, where instead of using Mach senders, I use rings because they're much better for WDM. You can see the ring here has some detuning and coupling efficiencies, and then at the receiver we have a broadband encoder. And sign detection here, so we can do positive and negative encoding. Now, if you look at the output of the result of doing this compute here, you end up with this problem where when we do this differential encoding, we get this kind of small photocurrent on the output of the photodetector because when we do differential encoding, we have a small output photocurrent on the photodetector, but both the photodetectors see a large amount of light hitting them. And so you have this what we call this fat zero problem, where you have a lot of shot noise you generate to get a weak signal out. And so in the case where you do differential encoding here, you have very poor signal to noise ratios typically, as opposed to if you just did single-ended encoding like we did in the paper. And so we tried to think about how to get around this problem. And this is not necessarily just like a netcast problem. There's actually a lot of approaches in the literature that try to do stuff like this for optical computing. And people don't really think about this as being a problem, but there are ways to get around this at an architecture level. So here we take the transmitter and we break it into parts. And if you just take your sign encoding and separate it from your amplitude encoding for the transmitter receiver, you can get a couple orders of magnitude improvement in signal to noise ratio and get rid of this fat zero problem. Again, happy to talk about it in more detail if folks are interested. Other Other thing is people might ask, you have all these wavelengths of light and you have some optical bandwidth you want to use. How many wavelengths can you reasonably pack in? Here we have a formalism that maps spectral crosstalk and temporal crosstalk. So when I encode data onto a laser of light, you broaden the spectrum of the laser by your data bandwidth. And then your modulators and photodetectors will have some bandwidth, temporal bandwidth at which they attenuate your perfect square wave signals. And we take these two formalisms and we map them together and we come up with this kind of domain here, where we see that below about 10% crosstalk, temporal or spectral, we get negligible impact on the performance of large machine learning models. This is like AlexNet, for example. And so this 10% crosstalk, if you map it back to something you care about, like channel capacity, you can see that you can operate across the entire optical C-band with 5.3 terawatts per second of throughput that you can use. So this is a good number. And if you could tolerate more crosstalk by making your models more crosstalk resistant, you could pump that number up. And so in summary of the talk, the thing that I've demonstrated today is photonic edge computing, where we make use of 2.4 terabit per second silicon spark transceiver made in a commercial CMOS foundry that can perform 8-bit accurate computing on sensor devices in real-world fiber deployments with 86-kilometer of deployed fiber across 3 terahertz of optical bandwidth. We also went on a weird nerdy tangent and showed off these time integrating receivers that have 10 attojoule per multiply energy efficiency and the ability in modern CMOS technologies to scale to less than 1 photon per multiply. All this enables teramultiplies per second of computing efficiency on real-world edge devices with milliwatt-class power consumptions. I thank all the folks on the screen who have been instrumental to the work, in particular, Dirk England's group at MIT and all the associated folks, as well as folks at Nokia, Lincoln Laboratory, and Lightmatter, and my funding sources. And I'll open for questions.
Yeah, thanks, Alex, for the great talk and your great work. It's very exciting to actually see this experimental demonstration, and also your insights for the photonic computing, both on the efficiency and the crosstalk robustness. Are there any questions from the audience? So before I go through the chat box, actually you have the chance to directly speak up and ask Alex. Okay, are there any direct questions from the audience?
Hello. Hi, Alex. Great talk.
Hey,
I wanted to ask you a question that's maybe a little bit speculative. That's more to hear your thoughts. If you could bring one material class to your next generation dream design, what would you pick? 3.5 gain, PCM for memory, something else? I'm kind of curious to hear your thoughts.
Yeah, that's a good question. So I'm very partial to 3.5 on silicon. So kind of the options here, your spectrum of options for what you want to add to silicon photonics to give it more functionality, is 3.5 materials for light generation, or Optical's material, lithium niobate barium titanate, for example, for high-speed modulation, or PCM, like programmable memories in optics. And the thing I'm most partial to is a 3.5 material. And the reason why is because having lasers and gain native in your platform really does enable a lot of applications that you couldn't do without before. In addition, the economics of 3.5 materials today is quite horrendous. So if you look at people like 3.5 foundries, how much they charge per wafer is just horrifying. For small 4-inch wafers. And so 3.5s on silicon through, for example, epitaxy or coupons or pick and place or whatnot, really does enable a future for photonics, not just in this application, but in multitude of applications that weren't possible before. So that's what I'm most partial to.
Got it. Thank you.
Okay, great. Yeah. There's a question in the chat box. For really large models, as you said, the memory bandwidth is the bottleneck, right? So is there any special solution from photonics to mitigate such a data movement bottleneck? For example, something like photonic memory store for in-memory computing?
Yeah. So the size of optical memory cells, be it memristors or or PCM or other, are really quite large compared to their electronic counterpart. You know, an SRAM cell is deeply sub-square micron in size. Same with HBM and some DRAM cells are quite small. And so electronics really does have quite a nice tool set for creating large arrays of memory. Where large here is the size at which I need to be able to actually store the weights of those models, right? Again, the number we're trying to hit here is 100 trillion. It's not 100 by 100 or 1,000 by 1,000 arrays of photonic components. It's substantially larger than that. And so you need to be able to store 100 trillion values in some distributed computing system to do best-in-class machine learning today. The answer is likely not PCM for storing the entire model, right? Now, there could be a role for something like PCM in keeping a subset of those weights local and then like updating them repeatedly. But for very large model sizes, you likely want to keep them in electronics. Where photonics might come and help here is how do I get those 100 trillion weight parameters and keep them local to some computing infrastructure, be the compute a digital ASIC or something in analog like a memristor crossbar array or a photonic processor, right? Co-packaged optics could really help you there.
Yeah. Great, yeah, thank you. Next question is more like a general. Should we construct some customized optical neuromorphic computing model based on the uniqueness of the hardware, or just make it more general, like the GPU, TPU, so we can be compatible with the general machine learning community for pre-trained DNA models?
Yeah, so my thoughts there are a bit non-academic and really quite boring. If you go to like a data center provider today and you kind of ask them, like, what do they want in hardware? They really want a black box that looks exactly what they've been using currently, right? You know, they want a thing that looks just like the NVIDIA GPU or whatnot that they've been using. And if you tell them that, hey, the computer I built for you is faster, more energy efficient, but it uses this funky new physics you've never heard of before, and also the entire software stack is different, and you need to retrain all of your models to run it, they'll just tell you no, right? You'll never gain any customers if you do that. So the thing you practically want to do is you want to create a black box. Ideally, you never tell anyone there's any optics in it at all, that is more energy efficient and higher throughput, but runs the same software stack as what your competitors are doing, be it, you know, PyTorch, Onyx, CUDA, like somehow if you can get CUDA to run on the thing, and ship that to customers, right? And so for that reason, I would say you probably want to make a raw matrix vector multiplier accelerator.
Yeah, I also think so. Yeah, thank you very much. Maybe I'll leave my own question at the end. So next question is like how much is the energy for the laser, and also based on your diagram, the photonic part in terms of area is much larger than the CMOS part. So it's only capable of processing a relatively small matrix. So how to handle a large model?
I'll ask you to repeat the second question. I'll target the laser one first.
Yeah.
So typically lasers are horribly inefficient, right? So a laser that you can buy off the shelf today with reasonable output powers and spectral and nice spectrums and whatnot is about 10 to 20% wall plug efficiency getting light into the fiber. If you wanted to do something like wavelength division multiplexing, you either need to buy a very large number of discrete lasers and have some control over them to put them at the right spectral spacing, or make use of a technique like an optical frequency comb to create your spectrum, your tailored spectrum for you. Optical frequency combs, if you go with these, if you design them right, can be let's say 50 to 60% efficient. So again, that hits your wall plug efficiency. But let's like work backwards from the receiver and go forward, right? So here, the thing I'm saying is you could make something in this particular architecture that's on the order of a photon per multiply, right? And accumulate. And so if I'm computing at 10 teramultiplies per second, so that's 10 to the 13 times 1 photon per multiply here. That means I need to do, I have 10 to the 13 photons per second that I need to feed into my receiver to do compute here. And the energy, that's for one wavelength channel. So multiplied by 100, it's 10 to the 15. The energy of a photon in the C-band is 10 to the minus 9, minus 19. So 100 zeptojoule. So you end up 10 to the 15 times 10 to the minus 19 at like 10 to the minus 4 optical power you need to pump in. So it's sub-watt across the entire C-band. Sorry, sub-milliwatt. It's like 100 microwatt across the C-band. So it's very reasonable amounts of optical power that you need to get to this receiver. With reasonable coupling losses and whatnot, you're likely starting with just about a milliwatt of optical power total across all your wavelengths at the transmitter that you need to be pumping into the system. So it's not high.
Mm-hmm.
Compared to the cost of the electronics here, ADCs and DACs,
Mm-hmm.
this energy cost is low. So it doesn't matter at the end of the day.
Yeah, sure. Yeah, maybe we can select one question for each person. So the next person asks a question, what's the precision for the DAC? And also, what limits the number of channels for your integral photonic accelerator?
What's the name of the person who asked the DAC question?
Yeah, the first one is the Mach precision. Is it 8-bit integer number or?
Yeah, sure. We operate, it's not necessarily an integer, it's like a floating point value. But yeah, here the precision is like an 8, it's comparable to an 8-bit floating point computation.
Floating point, you mean the standard IEEE floating number or general?
Not like an IEEE floating point, sorry. Just like if I wrote down real valued numbers on paper and then I rounded with 8 bits of precision compared to their maximum value of 1, that's the precision of this computation.
Oh, I see. So basically just 8 bits uniformly quantize the value.
Yeah, that's a good
not
way of
an
saying it.
integer. Okay.
Yeah.
So what limits the number of channels for the actuator? Because of large area. Previous student also asked the question, the area is quite large, so basically you can only implement 8 channels or 16 channels. So what kind of limits is this channel number?
Yeah, so here, this is a half reticle of silicon. So this is like 400 millimeters squared or so to cram all these optical modulators on. And you can see it doesn't make use of the full reticle, but this 48 wavelength channels is not by any means the limit to what you can cram onto a silicon reticle today. So if I look at what, for example, a co-packaged optics company like IRLabs is doing, they have on the order of 100 ring resonators going at 32 gigabit per second each that they can have on a size of silicon that is deeply below 100 square millimeters, right? So I think realistic, and that's doing digital encoding, so you need to add some DACs and ADCs to it to stabilize the devices with high precision. I don't think that's a fundamental limitation. It certainly should be possible to have, if my goal is to just create a single reticle of silicon that has a large number of high precision optical encoding channels for netcast, it should be definitely possible to do a few hundred different channels that I can encode on one reticle of silicon.
Yeah. So there are lots of some argument between the free space optics because they argue they can have 1 million pixels on the meta surface or the diffractive optical network. So which one is like more promising and practical for those scalable photonic computing for like AI or other applications?
Yeah. I think just stepping beyond netcast and just giving like a general comment, there's a lot of promise to be had in not confining yourself to doing everything in integrated photonics and trying to do a mixture, right? Free space optics has the benefit of being able to manipulate an enormous number of optical modes outside of a chip, but integrated photonics has the benefits of energy efficiency, compactness, whatnot. So if you can come up with systems that make use of integrated photonic transmitters and receivers to do your compute and encoding, but use free space in a manner to engineer how those devices map to each other, you likely can build a system that's much, much more high performant than the sum of its parts. You saw this. I'm gonna shell for myself again. There's a paper we had in PRX a couple of years ago on photoelectric multiplication, but kind of the really cool thing of that paper was not doing covariance detection to a compute. It was actually on free space sending of data from transmitters to receivers that enable you to scale out the size of these systems to large sizes. So I encourage people to like look at something like that or think outside the box. There's like good stuff to be had there.
Yeah, sure, yeah. Maybe you can like share the like articles to all the audience probably later. Yeah.
Yep.
And due to time limits, probably we'll take one more question. One more question is like, what's the most promising application scenario for this integrated photonic computing, and what are the key requirements for it to really show the system level advantage compared to the electronics?
What was the first part of that question? Sorry.
The first question is, what's the most promising application scenario for integrated photonic computing?
That's a good question in that I don't think there's one scenario that I could point to and say this is the best application to run here. I think likely you want to build a system that isn't pigeonholed into doing one thing, right? You want to make something reasonably general purpose for customers to like buy the thing, right? And so I would, if I were going to put my money somewhere, I would put it on building general purpose like computers, like matrix vector multipliers that target a host of different applications, including like large language models, image recognition, and whatnot, and be able to have a software stack that can compile all those onto the hardware. Software is reasonably cheap, hardware is expensive, so you kind of want to support a multitude of applications at once. Now, there is certainly an argument for like making custom accelerators for one specific thing, right? And where optics might shine there is data that's already in the optical domain and being able to manipulate that on a natively optical accelerator and make sense of the light in the world around you using a system like that. There's been some good work there that's been demonstrated, but I think we've yet to really find the killer application there where we need to say, yes, the only way we can do this is with a dedicated optical ASIC for processing.
I see. Yeah, since the follow-on question is like, he also asked, how can it demonstrate the system level advantage compared to electronics? So it can be in cloud computing, in data center, or edge computing. Because I heard more people like question the edge computing for photonics. They still think you should put a photonic accelerator in the data center, more reliable, stable environment for high throughput processing instead of edge computing with changing environment, unstable connections.
Yeah, I think it's a much harder business proposition, right? To put photonics in edge devices. You need optical access to them for the first part, right? Which can be hard, depending on the device. For some places, it's like rather straightforward content delivery networks and whatnot that are located close to you. That's like reasonably straightforward to get fiber to. But yeah, for a lot of sensors, it's quite hard to get optical access to them. Yeah, killer deployments are likely in data center in my mind, because of the willingness for data centers to adopt new technologies if they tick all the boxes. And also the data center, we talk about it as being a stable environment. It can be quite aggressive and challenging. but it is less aggressive and challenging than the real world and being deployed on the street, right? So there's certainly some benefits there.
Yeah, sure. Yeah, thank you. Thank you for your perspective. Yeah, probably due to time limits, we can have more offline discussion, probably in our Slack channel. Yeah, thanks everyone for joining the seminar, and also thanks Alex for the great talk and presentation, sharing with us your perspectives. Welcome to subscribe our mail list for our following seminar series. Okay, yeah, this concludes today's event. Yeah, thank you.
Thank you.
Yeah, thank you everyone.
Thank you guys for organizing this seminar. Can you please post the link of the Slack channel in the chat box? That would be really helpful.
Sure. Let me do it. Wait a second.
Or if you can display the screen where you have the QR codes for the.
Oh, right. That will be easier.
Would,
Yeah.
Yeah.
Mm-hmm.
I just wanted to thank you both for taking this initiative. I think it is something really needed for photonic computing community.
Yeah.
Yeah, thank you.
Yeah. Thank you. And we will organize the seminar like on a week, on a like monthly basis or 2 weeks approximately, and hopefully you guys will enjoy the future presentation. Yeah.
Yeah.
So
I'm
yeah,
expecting I'm expecting a presentation on squeeze light sometime in the future.
Yeah, I just share the screen. Yeah, probably you can scan the QR code if I'm sharing the correct screen. Okay.
Yeah, I got it.
Okay. Yeah. All right. I guess. Okay. I'm leaving.
Okay. Okay, I can stop sharing. Maybe we can end this Zoom session.
Yep.
Okay.
Okay. Bye.